What's up, boys and girls and everyone else? This is another science video lesson episode in chemistry for you. And for this episode, we will going to talk about the concept of three-gas law and its application. Come join me today as we go over this three-gas law concept as we put them together in one definite gas law formula, the combined gas law. Alright, so here we are in our lesson for this episode. So the combined gas law. So from the word itself, combined, okay, so it means that it has certain concepts. Okay, it has certain concepts here that are combined definitely to become one statement or one idea. Okay, so this is the combined gas law. So we will discover in this particular episode what are these things that are combined definitely to become one definite gas law concept. All right, gas law concept, it might be a statement or it can be a formula. So but before we start the discussion about this combined gas law that we have right here, I want to shout out special shout out to my students who are currently watching this video lesson. So I hope you will learn. At the end of the day, I hope that you will learn something on this video lesson and enjoy learning. All right, so let's go now with our topic that we have right here. Okay, so before we discuss the things about the combined gas law, let's take a look first on the gas properties. Okay, let's take a look first on the gas properties that we have in this gas law that we will going to discuss in this episode. So number one is gases have mass. All right, so even though we cannot see these gas molecules floating around us, okay, still the gases have mass. Okay, gases have mass. So we can see them, but definitely we can somehow find the mass of this gas. So that's the reason why krypton, neon, and argon, all right, so those gases have certain atomic mass. Okay, they have certain atomic mass, and one of the heaviest gases out there is the krypton. Okay, literally when you put krypton inside the balloon, instead of floating around, it will fall to the ground. Okay, just like a rock. Okay, so gases have mass. All right, next one, gases diffuse. Alright, so gases diffuse. Now, when someone sprays a perfume, okay, even though you are far away, you can still smell, the aroma of that perfume, okay, because gases tends to diffuse. They move from higher concentration to the area of lower concentration. That's how this, that's one of the very interesting property of your gas. They tend to diffuse. Alright, so the next one is gases expand to fill their containers. Okay, so what does it mean? It tells us that gases have volume. Okay, unlike liquid, alright, when you put liquid inside the container, it will fill out the container. Then the volume of the container is the volume of the liquid. It is the same thing as gas. Alright, it is the same thing as gas. When you put gases inside the container, the volume of the container is the same thing as the volume of your gas. If you want to find out the volume of the gas, compute the volume of the container. Alright, so gases expand to fill their container since they are moving. Alright, so since they are moving. Okay, next one, we have gases exerts pressure. Okay, so gases exerts pressure. So if you have a soft drinks in can, okay, if you are familiar with the soft drinks in can, when you shake that soft drinks in can, when you shake it, it tends to get sturdy. Alright, that the can itself gets to become sturdy. Okay, because of the pressure exerted by the carbon dioxide gas inside the can itself. Okay, so the carbon dioxide gas inside the can exerts pressure on the wall of the can. That is the reason why you cannot crush the can, especially when you after shaking it. Okay, after shaking the can, you cannot crush it with your with one hand. Okay, some people can crush it with two hands, something like that. But once you open that can, the can will now become you can now crush the can even with one hand. Okay, because the pressure exerted by the carbon dioxide is somehow dissipated. Okay, on the can. All right, next one is gases are compressible. Okay, gases are compressible. That's the reason why, okay, there is what they call scuba diver's tank. Okay, the tank behind the scuba diver. Okay, those are filled up by compressed gases. Okay, so we can mix up gases. We can mix up gases in certain okay, in a given amount of in a given amount of volume. All right, once you compress the gas, definitely you can decrease the volume. Okay, now when you decrease the volume of the gas, you can add another kind of gas. You can add another kind of gas, and you can, once you compress that one again, you can add another one. So meaning to say, if you want to put certain amount of gases, certain kinds of gases in one container, you can do so because gases are compressible. So you can mix oxygen with nitrogen, or even you can mix nitrogen, oxygen with carbon or helium, something like that. So those gases will not mix. Okay, those gases will not mix. The good thing there is, those gases, the oxygen can be compressed, the nitrogen can be compressed, and the helium gas can be compressed in just one container. Okay, so that's one interesting thing about gases. So that is, gases are compressible. And finally, alright, finally we have pressure and temperature are dependent to each other. So as you increase the temperature, the pressure of the gas will increase. So we will try to find it right here. Okay, so what idea constitute this property that we have over here? So the pressure and temperature are dependent to each other. Okay, so we have here the gas variables. Okay, so if you don't know what are the gas variables or what are the measurable properties of gas, so click the link above. So that is one of my video lesson right there. So if you don't have any idea what is this gas variables all about, okay, this right there. Okay, so the first one that we have right here, since gases expand to fill their containers, so we have volume. Alright, so we have volume. So the unit of volume commonly used in gas is liters. Okay, most or sometimes it is cubic meters, cubic centimeters, or milliliters. Okay, so those are the units of volume. Okay, but most of the time it is in liters. Alright, so next one is the amount. Alright, so the small n that you have right there. Okay, so the amount of gas is measured in moles. Okay, so a mole, or in some cases the unit of it is MOL. Alright, so MOL. Okay, so that's the gas. By computing the molar mass of the gas and the mass of your gas itself, okay, the actual mass of the gas itself, you can compute the amount of particles that the gas contains. Okay, and the particles that the gas contains is usually in this unit. Okay, mole or MOL. Alright, so the next one is temperature. Alright, so gases do not use the basic unit, or the basic unit of temperature gases use is Kelvin, because Kelvin is the one that can, or is the best unit of temperature that can explain the movement of molecules. Okay, so temperature of gas is always in Kelvin. Alright, next one, the pressure. The pressure units can vary. Alright, so the pressure units can vary from one unit to another. So all you need to have here is for you to convert. Okay, if you have two different units of gases, in terms of pressure, you can convert it from one unit to another, or you can go back to another unit, okay, by converting it. So the units are the following. So we have millimeters of mercury, we have kilopascal, okay, in honor of Blaise Pascal. All right, so okay, so we have atmosphere. So most of the time, some problems uses the most, or one of the simplest unit here, which is the atmosphere. Okay, and most of the time, or sometimes, they use torr. Okay, torr is somehow in honor for a scientist who named Evangelista Torricelli. Alright, so Torricelli. So there are conversion factors that are required for you to remember, okay, in order to convert this pressure from one unit to another. So These are the gas properties and gas variables that you need to know first. That you need to know first in order for you to understand what is the next topic that we will have right here. Alright, so that's it. So that is the gas variables and gas properties. Alright, so here we are in our first concept, okay, that constitute your combined gas law. Alright, so the first concept here is the Boyle's law. Alright, Boyle's law was formulated by Robert Boyle. Okay, hence we have the Boyle's law here. Now, he found out that pressure and volume are related to each other to a certain experiment. Now, using that particular experiment, he concluded that pressure increases when the volume decreases. So, at constant temperature and the amount of gas that you have on your system. Okay? So, pressure increases, then volume decreases, or vice versa. So, he found out that there is an inverse proportionality between the two measurable properties that we have right here. Okay? So, pressure is inversely proportional to your volume. Okay, so hence at the end of the day, Robert Boyle gave the idea, alright, so gave the idea that pressure and volume are related to each other inversely. So okay, so we have it right here, the formula of your Boyle's law. Okay, so we have here the 1 represents the initial, then the 2. Alright, so the subscript that you have right here. Alright, so the subscript that you have right here, the 2 means final. So 1 is initial and 2 is final. Alright, so P1 times V1 is equal to P2 times V2. So this is the formula for the Boyle's law. Okay, so let's take a look on how this formula works. Okay, now in Boyle's law, the product of pressure and volume is constant. Okay, the product of volume and pressure is constant as long as the temperature, very important here, as long as the temperature and the amount of gas doesn't change. Once these two change, Boyle's law is not applicable on that. Alright? Once the temperature and the amount of gas change in your system, Boyle's law will not be able to contemplate on that. Alright? So, as far as you can see on our example that you have right here, as the temperature, or rather pressure, as the pressure increase, okay, as the pressure increase, it still have the same constant value that is computed. Okay, even though the volume of your gas decreases, like the one that you have right here, from 8 liters to 2 liters, still it gives us the same constant computed value, which is 16 atmosphere liters. Now, what will be our expectation on P4 and V4? Alright, so we can safely say that at 1 atmosphere and 16 liters, okay, 16 liters of that gas at 1 atmospheric pressure, so it means that it has the same constant value of 1 atmosphere as well. Okay, so if it is 32, alright, if it is 32 and then 0.5, alright, so on P5, alright, and V5, so the atmosphere will be 1.5 atmosphere and 32 liters. So again, it's still the same. Okay, 1 atmosphere liter. Okay, so it gives us the constant value as long as the temperature and the amount of gas will not change. Alright, so now these are some examples of Boyle's law. Okay, so in real life, so the first one that we have right here is the bicycle pump. Okay, so the bicycle pump, so in order to increase the amount of air inside that pump, you need to decrease the pressure. Okay, you need to decrease the pressure. Now when you increase the pressure, the volume of gas, okay, the volume of gas is stuck in the inside the bicycle pump decreases. Alright, so the next one is the syringe. Okay, so the syringe, you can compress the gas there and affects its volume. Okay, so by the use of this plunger that you have right here. Okay, in the scuba tank, okay, the pressure inside the scuba tank decreases as the volume of the gas inside increases. All right. Once the volume decreases, then the pressure. All right. So then the pressure of the gas that you have there increases. Okay. So that's the reason why the divers is capable of staying underwater. It's because of these changes in the volume and pressure of the gases inside the scuba tank. Okay, so what is what is more profound right here is the lungs and then the underwater fish over here. So how is it possible that the underwater fish is one of the application of Boyle's law? Okay, in an underwater fish, we have a part there called the swim bladder. So this is the swim bladder. Okay, all fishes have this swim bladder. All right. So the swim bladder enables the fish to float on the surface and dive underwater. Okay, so once this bladder filled with air, okay, once the volume of the air increases, so the pressure definitely decreases. So what happens here? The fish will float up. Okay, so that's the thing there. When the fish expels the air from the swim bladder, definitely it will float down. Okay, so it will float down. Okay, so that's the effect of swim bladder to this fish that you have right here. That's the reason why when you have an aquarium, if you observe the fish there, it can go up and then it can go down. So it's a matter of how the fish manipulates the air inside its swim bladder. Okay, so another one is the lungs. Okay, now when the air pressure inside the lungs decreases, definitely the volume increases. So what is that? That is inhale. Alright, so during inhale, the pressure inside the lungs decreases, then the volume of air inside the lungs increases. Okay? So there's a difference in pressure. So pressure here inside the lungs. Alright, so pressure here inside the lungs decreases. Okay? So pressure inside the lungs decreases and yeah. Alright, so pressure inside the lungs decreases and the pressure outside our body increases. Okay, so there's a differences in pressure, so that's the reason why the air will go inside. Okay, because of that differences in pressure. Now, when you exhale, what happens is, alright, so what happens when you exhale is the pressure inside the lungs increases and the pressure outside your body decreases. Alright, so there's less pressure outside your body. So what happens here is you expel the air out of your lungs. Okay, you expel the air out of your lungs. Okay, so that's how the lungs work, and that's how the lungs uses the Boyle's law for it to work. Alright, so these are the classic examples in daily life of Boyle's law. Alright. Okay, so in order for us to appreciate what is Boyle's law all about, so let's try some sample problems that we have right here. Okay, so I have some sample problems. Here that we will going to compute. Okay, so if you want to pause this video, then by all means do it. Okay, then then play it afterwards, and if you want to find out if your answer is correct, play it afterwards, and see to it. Okay, observe your answer, observe your solution, where did you make mistake and something like that, in order for you to find out how to do this, okay, or how to manipulate or how to answer certain word problems related to Boyle's law. Okay, so let's start with this one. So Freon 12 CCl2F2 is used in refrigeration system. Okay, refrigerator and air conditioning system contains Freon 12, and that is a refrigerant. That is one important part or ingredient of your refrigeration system, or part of the refrigeration system. Without this Freon 12, the aircon and the refrigerator will not cool. Okay? it will not give it will not lower down the temperature. Okay, that is impossible without Freon 12. All right, so what is the new volume of 8.0 liter sample of Freon gas? Initially at 550 millimeters of mercury. After its pressure is changed to 2,200 millimeters of mercury at constant temperature. Alright, so let's solve for this one. Okay, so the first thing that you need to do here is to find out which one is the pressure 1 and which is the pressure 2, as well as the volume 1 and also the second volume that you have right here. Okay, so definitely the pressure 1 is present in this problem via context clue. So initially, okay, so that is your context clue. Okay, so initially, so meaning to say that this number is your pressure 1. Okay, so 550 millimeters of mercury. So whereas the second number that you see here in this problem is the pressure 2. Okay, there you go. Okay, so the next one, the volume 1. Okay, so the volume 1. Since when you read the problem, there's a word new here. So it means that in context clue, meaning to say this is the volume or the final volume that we are looking for. Alright, so definitely we are looking for the final volume. So that is why this is the new volume. And the number that you have over here is your first or the initial volume. So 8.0 liters. Alright, so there you go. Okay, so what do we have right here? Okay, so what do we have over here? Okay, so we will use the formula provided to us by Robert Boyle. So we have P1 V1 is equal to P2 V2. Then we will derive this formula. So since V2 is missing, so we have V2 is equal to P1 V1 over P2. Okay, so that's how simple it is to derive the formula that we need here in this problem. Okay, so let's work on the problem. So mmHg, and we have the volume, which is 8.0 liters over 2,200 millimeters of mercury. Alright, so we have the V2. So if we will compute this one, so 550 times 8 divided by, okay, so that will be 2.00 liters. Three significant figure. So 2.00 liters, 2.00 liters is the volume of the Freon. Okay, so that's the complete answer for this problem that we have right here. Okay, so the one that you see here right now is the final answer for this problem. Okay, so 2.00 liters is the volume of the Freon. Alright, so did you get the right answer? Okay, do we have the same answer? Okay, so comment down on the section, comment section below. Put your comments in the comment section below. So let me know if you got the correct answer. Okay, next problem. Now, a sample of oxygen gas has a volume of 12.0 liters at 600 millimeters of mercury. What is the new pressure when the volume changes to 36.0 liters at constant temperature and amount of gas? Okay, so again, we just write up the variables that we see on the problem. So we have volume 1 and the final volume and initial pressure and the final pressure. Alright, so what is the first volume? Alright, so the first volume is definitely this one. Okay, definitely this one. So that is 12.0 liters. So probably, or more so, that the 36.0 liters that you have right here is the second volume. Okay, so next one, we have the pressure 1. So what will be the pressure 1? So if you take a look at this word, so meaning to say that the pressure 2 is the one missing, and the 600 that you see here on this problem is the second or the first or the initial pressure. Okay, so let's take a look. So again, we will use the formula. And since pressure 2 is missing, we can find out the pressure 2 via V1 over V2. Okay, so this is the pressure, the final pressure that we are looking for. Okay, so we have 600. Okay, and volume 1 is 12.0 liters over volume 2, which is 36.0 liters. Okay, so 36.0 liters. So okay, so there you go. So we have to cancel the liters that you have right there. So 600. Okay, so 600 times 12 divided by 36. So that will be 200. All right, so 200. Okay, 200 millimeters of mercury is the pressure of the O2 gas. Okay, so that will be your final pressure. Now let's take a look if this answer makes sense. Okay, so before we leave this particular concept, let's take a look if the answer makes sense. Okay, so in V1, the volume is 12. So V1 is larger or smaller than V2. Okay, so it means that it has a higher pressure. So it does. Okay, it does have a higher pressure. So at 36, okay, at 36 amount of volume, at 36 liters, we expect that the pressure should be less. Okay, less than the initial pressure. So we got 200. So it was less than the original pressure. Okay, so definitely this formula works. Okay, the inverse proportionality of this formula works. All right, so this is the Boyle's law. All right, so after the Boyle's law, we have another concept that we have right here. But before I reveal what concept is under the concept number 2. Okay, so let's watch this one. Okay, for you to have an idea on what this concept is all about. Okay, so I know you are familiar with Crazy Russian Hacker, so I'll put the link in the description below. So if you want to watch his video about what happens if you freeze balloon. All right, so let's take a look.
What's up everybody, welcome back to my laboratory where safety is number one priority, and today we're going to put balloons into the liquid nitrogen and let's see what happens. Okay, once again I got here liquid nitrogen. I'm gonna pour it in a bowl.
Alright, so just a great trivia about liquid nitrogen. Liquid nitrogen is the same as the nitrogen gas that you know. When you subject the nitrogen gas into a tremendous amount of pressure, it changes into liquid. Okay, so it changes into liquid. So that's how your liquid nitrogen is brought into place here. And liquid nitrogen has a has a lower temperature state. Okay, so the vapor that you see here is the nitrogen gas. That nitrogen gas that these are the nitrogen that becomes a gas, okay, in this liquid form that you have over here. Okay,
Whole bunch of it. Look at that, so cold.
All right, so that is the liquid nitrogen. It is very cold. Okay,
Put that away. Okay, and now I'm just gonna put these balloons inside of it. Let's see what happens.
Alright, so before we play this one up, so let me ask you and then put your answer in the comment section below. So what do you think will happen to the balloons if you put it in the liquid nitrogen bath that you have right here? Okay, so let me know what you think will happen. Okay, so let's play and find out what will happen to this balloon.
Actually, I need something to push it in. Whoa, look what happens to those balloons.
Alright, so
That's so
actually Actually, you can work this one at home as well. You can buy a balloon, then inflate that balloon, then put it in your freezer. Okay, you don't need a liquid nitrogen for this one. Your simple freezer can help you understand this simple activity that you have right here. Okay.
Wow, this is so awesome. Too much fun.
Alright,
Wow,
so
it turns out.
if you said that the balloon will deflate, okay, when it is put in the liquid nitrogen bath that you have right here, if you said that the balloon will deflate, then you are correct, okay, on your hypothesis. Now, the question here is, what happened to the gas molecule? Alright, so what happened to the gas molecule as the balloon deflates in this setup that you have right here? What happens to your gas molecule inside the balloon? Okay, so let me know in the comment section below this video. Okay, what is your thoughts, or what are your thoughts about that one? Okay, let's play it again.
Like a paper. They don't even pop, so they kind of deflate.
Alright, as you can see, it deflates, okay, when it is put inside the
wow,
liquid nitrogen
so
bath.
Awesome. Couple more. There's yum. So definitely to help it for it to deflate faster and sink it in. Let's try a bigger one.
Alright, even the biggest
I used
balloon.
a little bit too much of a liquid nitrogen. Maybe I'll just pull it back when I'm done.
Okay, so even the biggest balloon that he has.
This balloon is shrinking as well. There you go. Oh,
Alright.
Stuck.
So
No, don't get stuck.
it gets stuck.
Whoa, this is insane. Do you
Alright,
hear it
definitely
crumble up?
insane.
So crazy. Okay, now what I'm gonna do is put it aside.
Alright, so hypothesis time once again. What will happen to your balloon when it returned? Okay, when you return the balloon into its normal room temperature. Alright, so again, the question is, what will happen to your balloon if you put it back in the normal room temperature? What will happen? So write it down in the comment section below this video. Okay?
And guess what? I'm just gonna pull them out and put them right here, and let's see what happens. Look at them. This is like Terminator 2. Remember that when he
Alright, Terminator.
put back together the liquid one? Whoa, look at that. This is so awesome.
Alright. Oh, yes, it is awesome.
Woo! One of them popped.
Alright, so if you're
That's
going to
kinda
ask why the other balloon popped, because the liquid nitrogen affects the integrity of the rubber. Okay? The rubber that you have right here is not anymore the same as the integrity of the rubber before he puts it inside the liquid nitrogen bath that you have right there. So the temperature affects the integrity of the rubber. Okay? That's why it didn't go back, or it didn't deflate anymore. Alright?
Yeah, look, I can even
Or
hold
inflate
it.
rather.
And because I'm holding it, it's actually... Ah! That's so scary when they pop. That's kind of awesome.
So now that ends up this particular certain experiment that you have right here. Okay, so the question here is, what happened to the gas molecule? Okay, earlier we saw that the balloon deflates. And right now, as it returned to the normal temperature or regular room temperature, as it returns to the room temperature, it deflates, or it inflates once again. Okay, so what do you think happened inside this balloon that you have right here? Alright, so the answer to those questions is in this concept that we have over here. Okay, so let's go back to our board. Okay, so the concept number 2, based on that experiment about the balloon by Crazy Russian Hacker. Again, the comment is, or the link is in the description below this video. You can visit his channel and watch his experiment about different things. Okay, so the concept number 2 is all about The concept number 2 is all about the Charles law. Okay, so the Charles law. This was formulated by Jacques Charles, and he found out that the temperature and volume is related to each other. Okay, so how do they become related to each other? So he found out that as the temperature increases, the volume increases. So as the temperature increases, the volume increases at constant pressure and amount of gas. Okay, so what is the relationship that we have right here? That is directly proportional. Alright, so that is directly proportional. So pressure, or rather volume, is directly proportional to temperature at constant P and N. Okay, so definitely, alright, so that is your formula, okay, given to us by Jacques Charles. So that's the relationship between volume and temperature. So as the volume increases and the temperature might or is likely to increase as well. Okay, now what is the thing that we have right here? The temperature that is used right here is not in Celsius, it is always in Kelvin. Alright, so the temperature that is used here is always in Kelvin. So let's try to find out what are the other things behind this concept that we have over here. Alright, so one of the example or one of the application of Charles' law is the one that is floating right there. That is the hot air balloon. Okay, one of the things that you should take note of about the Charles' law. Okay, so the law says that at constant pressure, volume of a fixed number of particles of gas, again, constant pressure and number of particles of gas must be constant. It is directly proportional to the Kelvin temperature. Mathematically speaking, it looks like this. Okay, so alright, so V is for volume, and the K is for Charles law constant, and we have the temperature, which is the capital T on your formula. Okay, now what is the idea? What's the big idea here? Now, as the temperature is increased, okay, the gases fill the greater volume as long as the pressure remains constant. Okay, so as the temperature increases, the volume increases. So why is that possible? Okay, why is that possible? It has something to do with the kinetic energy of the molecules of your gas. It has something to do with the kinetic energy of the molecules of your gas. So that's the reason why the volume increases once the temperature is increased. Okay, so later on we will try to find it out why. Alright, next one. Gases expand at constant rate. Alright, and the rate of expansion is similar to all gases. Okay, all gases, carbon dioxide, oxygen, helium, or whatever it is, as long as it is gas, they all have the same rate of expansion. They all have the same rate of expansion. Okay, so given to us as the rate of the temperature. Okay, as the temperature increases, this rate of expansion is constant to all gases. Okay, so okay, let's try to find out why. Okay, now what will happen if you double the temperature? If you increase the temperature twice, so what will happen? So definitely the volume also will increase twice. Okay, so that's how the direct proportionality works. Okay, so definitely we can modify the Charles law to become what you have seen a while ago. So K is equal to V over T. Okay, so that's the thing about this Charles law that you have right here. Now the question here is, why is it that Kelvin is used rather than Celsius? Okay, or even Fahrenheit. Okay, why is it Kelvin used? Okay, now the Charles law is talking about the kinetic energy of the molecules of your gas. Okay, now as you can see here, we have a very straight line slope that you have right here on this graph. Now this graph is all about kinetic energy versus temperature in Kelvin. Alright, so we will try to find out why Kelvin is used rather than degrees Celsius. Okay, so as you can see here, the Kelvin temperature is very good in describing the movement of molecules in terms of kinetic energy. So as you can see at absolute zero, or 0 Kelvin, all molecules or all movement of molecules stops. Okay? All movement of molecules is stopped. So definitely this is one great thing of using Kelvin as unit for temperature rather than Celsius. Alright, so as you can see here, as the temperature in Kelvin increases, the kinetic energy of the molecules, whether it is gas, liquid, or solid, it increases as well. Alright, so they are directly proportional to each other. Now, let's take a look. Okay, let's take a look. What if we use degrees Celsius? Alright, so as we all know, 0 degrees Celsius is the freezing point of water. Alright, that is the freezing point of water. That is around 273.15 Kelvin. Alright, now if we will going to plot this in this graph, so 0 degrees Kelvin is or 0 degrees Celsius rather is somewhere located at the middle. Okay, so this is the 0 degrees Celsius. So as you can see here, the 0 degrees Celsius doesn't describe the motion of your molecules, because at 0 degrees Celsius, molecules is still moving. Okay, so as you can see on this graph, so molecules are still moving at 0 degrees Celsius. So the molecules inside your eyes, okay, the molecules of water inside your eyes is still in constant motion, but not that fast, but they are starting to get slower and slower. Okay, now when we take a look at 100 degrees Celsius, that is around 373.15 Kelvin. So it is somewhere right here. Alright, it is somewhere right here. So if you can plot this graph, as you can see, there's no sense on using the degree Celsius as the basis for the kinetic energy of the molecules. Okay, because at 100, still the molecules has a higher kinetic energy, okay, than the previously 0 degrees Celsius that we have. Okay, so the problem with degrees Celsius is it has negative values. Okay, whereas the temperature in Kelvin, it doesn't have a negative value. Alright, if it has, well, it is not yet found if there is a negative Kelvin or negative temperature in Kelvin that is found outside our planet or something like that. So as of now, we all know that the lowest temperature available is absolute zero. Okay, that is the 0 Kelvin. Okay, so that's the problem of degrees Celsius. So we have negative, okay, we have negative values. So that's the reason why Kelvin is used, is because it is absolute. Okay, the value of temperature in Kelvin is absolute. Okay, just like in math, the absolute value, it is neither negative nor positive. That is the absolute value of a certain number. Alright, so okay, another reason. Now if you will compare, alright, if you will compare the the value that you have right here of the kinetic energy, when you double the value of the temperature, for example, you have 1000 over here, we will double it to become 2000 Kelvin. So the kinetic energy of 1000 Kelvin is 40. Whereas, the kinetic energy of the 2000 Kelvin is somehow on the 80th mark of the kinetic energy. Okay, so somehow it tells us that if we double the temperature, we double the kinetic energy. Okay, the molecules starts to move very fast. Okay, so what if we do that? We do the same thing on Celsius. Okay, 200 degrees Celsius is equal to 473.15 Kelvin. And again, 473, we didn't pass 500. Alright, so then again, we cannot say that the 473.15 Kelvin is when we double the temperature at Celsius, it means that we double also the kinetic energy. So based on our results that you have right here, it doesn't work that way. Okay? So degrees Celsius is not a good unit for describing the kinetic energy for certain molecules. Okay? That is arbitrary. Okay? The Celsius is arbitrary, whereas temperature in Kelvin is absolute. Okay? So those are the reasons why we use Kelvin instead of degrees Celsius. Now, this is how the graph looks like. So the Charles law, okay, the graph or the slope of the graph of your Charles law looks like the same as your kinetic energy versus temperature graph that we have a while ago. Okay, so it is in a straight line. Unlike in Boyle's law, the pressure and the volume exponentially drops because that is in a parabolic format that you have right here. This is a parabola. It means that the drop, okay, once the pressure increases, the drop of volume or the volume that you have right here is exponentially decreasing. Okay, so that is the Boyle's law. Whereas in Charles' law, when you increase the temperature, the volume will increase at a constant rate. Okay, so at a constant rate. So that's the difference in terms of the slope of Boyle's law and the Charles' law that you have right here. And what does this one tells us? This tells us that Charles' law, okay, the volume increases due to the fact that the kinetic energy of the molecules of your gas increases as well as the temperature increases. Okay, so that's the concept behind this. Okay, now what are the examples of Charles' law? Okay, number one is tires. Okay, you know the reason why tires have an allowance? You know why tires have an allowance inside? Or some people do not want to fill out, okay, completely their tires, okay, into maximum volume. Okay, why do these people left some allowance for this thing, for this tire that you have right here? It's because when your tires are subjected to heat, the gases inside your tires increases, or the volume of gas inside your tires increases. So in order to accommodate that expansion, the allowance is very important. The allowance that you left there on your tires are very important in order for your tires not to explode. Okay? Alright, next one, we have here the hot air balloon. The hot air balloon will not fly if the temperature of the air inside the balloon is lower. Okay? So that's the reason why there is a fire. Alright, so there is a fire needed in order to expand the gas inside the balloon. Okay? So, as we all know, warm air rises, cold air sinks. Okay? So, you learned that one from earth science. That's the connection between earth science and chemistry. Alright? So, that's the reason why air conditioning system is placed on top of your wall, because cold air sinks and the warm air rises as its usual pattern. Alright, so another one, the bread. So if you were going to ask, why is bread part of the examples of Charles' law? Okay, why bread is an important example of Charles' law? Because the bread will not rise, or the dough. Okay, before it became a bread, it is a dough. Okay, the dough will not rise if there's no Charles' law, because the temperature, okay, when you heat up your dough, the carbon dioxide that it will be produced during the fermentation process will expand, and it allows the dough to expand to become a bread. Okay, so the one that you have right here. So that's the reason why the bread have a lot of holes. If you notice when you eat a bread, there's a lot of holes on it. Okay, there's a lot of holes on it. Those are the holes where your carbon dioxide passes through as it expands. Okay, as your bread expands, your carbon dioxide also expands inside. Okay, so that is the example of Charles' law that we have right here. So not only the bread, but also the ping pong ball. We have the helium balloon and some floaters. Alright, so some floaters are very good examples of Charles' law. Another one, we have here the lungs. Okay? As the volume increases inside your lungs, the temperature of air inside your lungs increases as well. So that is why when you exhale, alright, so that's the reason why when you exhale, the temperature of the air that you exhaled is higher than the one that goes inside. Okay, so that's a good fact that we have right here. Okay, so these are the very good examples of Charles' law that we have right here. Alright, so let's work on some sample problems related to Charles' law. Again, you can pause this video. You can pause this video if you want to answer it independently. Alright, so first problem that we have right here, a balloon has a volume of 785 milliliters at 21 degrees Celsius. If the temperature drops to 0 degrees Celsius, what is the new volume of the balloon? Okay, so what is the new volume? Okay, only to find out, alright, we will find it out only if we compute this. Alright, so we have volume 1, volume 2, temperature 1, and temperature 2. Right, so there you have it. Alright, so what is the volume 1? Okay, so volume 1 definitely is this one, because on the problem it says that it needs a new volume. So definitely this will be your final volume, which is the unknown. Okay, so the 785 ml is our first or initial volume. Okay, so we have the temperature. So we have 21 degrees Celsius. Now, what is very important here is that you do not use Celsius. Alright, you do not use Celsius. Convert it first to degrees Kelvin. So 21 plus 273.15. So that is 294.15 Kelvin. Alright, so how did I get this one? 21 plus 273.15. Alright, more so, at 0 degrees Celsius, the conversion of that into Kelvin is 273.15 Kelvin. Okay, so there you go. Okay, so everything is converted. So can we convert the volume? Okay, no need, because the problem doesn't tell us to convert it into liters. So let it stay that way. Okay, let it stay that way. So we have volume 1 over temperature 1, then volume 2 over temperature 2. Okay, so this is the formula provided to us by Jacques Charles. Okay, and since we are looking for volume number 2 or the final volume, so the formula that we will going to use is based on this formula. So we have okay, so okay, so V1 times T2 over T1. Okay, so that will be the formula that we will going to use. Okay, so let's plug all those variables that you have over here. 785 ml times 273.15 Kelvin over 294.15 Kelvin. Okay, so there you go. Okay, so cancel the Kelvin unit. So we are left with milliliters. So we have volume 2. So that will be 785 times 273.15. So that will be divided by 294.15. So that will be 729. Okay, 3 significant figures, 729 ml. Okay, is the new volume of the balloon. Alright, so that will be the new volume of your balloon, 729 milliliters. Okay, so is the answer make sense? Let's take a look. Okay, so at initial volume, we have 785. Okay, and temperature 1 is higher than the temperature 2. Okay, so we expect that the temperature 2 will give us a lower volume. So let's see. Alright, so from 785, it becomes 729. So definitely, direct proportionality of this formula works. Okay, now, if you're going to ask, what if you forgot to convert it into Kelvin? What will happen? Definitely, your answer is incorrect. Alright, so your answer is incorrect. Why? It's because this is 0 degrees Celsius. Okay? This is 21. Okay? This is 21 degrees Celsius. So, 785 times 0 is 0. And then 0 divided by 21 is also 0. So, it means that our volume or final volume is 0. Alright? So, that is impossible. Okay? So, that is impossible. Your volume or the volume of the gas suddenly went missing. Okay? So, always, okay? So, reminder to everyone, always convert the temperature to Kelvin. Alright, so let's take a look at the second formula that we have, or second problem that we have right here. Alright, a sample of oxygen gas has a volume of 420 milliliters at temperature of 18 degrees Celsius. At what temperature, at degrees Celsius or in degrees Celsius, will the volume of the oxygen be at 640 ml? Alright, so let's answer. Okay, let this problem. Hey, we have V1, V2, we have T1 and T2. Okay, so let's try to find out what is the V1. Okay, what is the V1? So probably V1 is this one based on our based on how you read this problem. So the first number that you encountered, that the first volume that you have encountered here, probably that's the V1, right? So 420 ml. And the second or the last volume that you see here will be probably the second volume, that is the 640 ml. Alright, so if you're going to ask, the problem is asking the temperature in, or is looking for the temperature in degrees Celsius. Why not use directly this number that you have right here? Okay, is that possible? No, you must convert it into Kelvin. Okay, you must convert it into Kelvin before you do computation, or else your answer will be incorrect. Okay, so let's convert. So we have, probably this is the temperature 1, so we are looking for the final temperature. So 18 plus 273.15. Alright, so we have right here the variables. So we will going to use the same formula that is that we used on the first problem that you have. So we have V1 T1 over T1, V2 over T2. Okay, so since we are looking for the final temperature, so okay, so we can use T2 is equal to V2 times T1 over V1. Alright, so this will be the formula that we were going to use based on this formula that we have right here. Alright, so let's take a look at the variables. So let's put it right here. So 640 ml multiplied to the T1, which is 291.15 Kelvin over 420 ml. Okay, so that will be the value here. Okay, let's compute. So 640 times 291.15. Okay, so divided by 420. Okay, so we have 443. So we have 443. Okay, 0.657 Kelvin. So this is the answer, but it is in Kelvin. So in the problem, we are looking for the temperature in degrees Celsius. Okay, so we must convert this one into degrees Celsius. So minus 273.15. So the answer will be, alright, so the answer will be, so don't forget to include all the decimals so that you will not have any problem with your final answer. Alright, so that answer will be 171 degrees Celsius is is the temperature of the oxygen gas. Alright, so that will be your final temperature. Alright, so that is 171. So did you get the right answer? Okay, so did you get the right answer on both sample problems regarding or related to Charles's law? So if you got the two problems with correct answer, let me know in the comment section below this video. So if you are confused with something, so let me know. You can ask your question also in the comment section below this video. Alright, so that is the sample problems related to Charles's law. Alright, so here we are in the third and final concept before we combine them all together to form one definite gas law. Alright, so in the concept number 3, this third concept is best seen on your kitchen. Okay, best example of concept number 3 is the pressure cooker. Okay, so the pressure cooker. Now, did you know that the pressure cooker is a cooking utensil that can be used to cook food at a smallest amount of time? Alright, in the shortest amount of time, you can cook your food relatively on high temperature. You can cook your food on high temperature and cook your food in the shortest amount of time. Okay, especially your pressure cooker can be used to cook meat, okay, pork or beef, something like that. Okay, so after cooking this meat, okay, the meat will become tender, or will become it will be tenderized because of the tremendous amount of pressure built inside the pressure cooker. Now, what is this third concept all about? Okay, so the third concept that we have right here, alright, so the third concept that we have right here is the Gay-Lussac's law. Alright, so this is not made up of two persons. This law is not made up of two persons or two scientists. Right? So this Gay-Lussac's law was made by Joseph Louis Gay-Lussac. Okay, he is a French. Alright, so Joseph Louis Gay-Lussac. Okay, so he found that the temperature and pressure in accordance of kinetic molecular theory. So as the kinetic energy of the molecules increases when the temperature increases, okay, there's a relationship on it into pressure. So definitely when the molecules starts to move faster, there's something happen. The pressure increases. Okay? So definitely the pressure and temperature, according to him, is somehow related to each other, and that is directly proportional as long as the volume and the number of moles is constant. Okay, so as long as these two is constant, so pressure is directly proportional to temperature. Okay, so pressure is directly proportional, and that is the formula that we have right here. So pressure 1 over temperature 1, pressure 2 over temperature 2. So this is the formula given to us by Joseph Louis Gay-Lussac. Okay, so let's find out what is more about this thing, or this formula. Alright, so this behavior would be expected in the assumption of kinetic molecular theory. Number 1, gases move in a constant or straight line and in a random motion. Okay, now when you increase the temperature, the kinetic energy of the molecules also increases. So definitely the speed of these gas molecules also increases. So they are moving in a super fast manner. Okay, so this causes the collision with the walls of the container, which is somehow forceful. Okay, which is somehow forceful. So that's the reason why. This is spray can that I have right here. Okay, so this is spray can that I have right here. It has a tremendous amount of pressure inside. Okay, it has a tremendous amount of pressure inside. So because the gas inside this spray can, contains a lot of pressure, and it hits the wall of this spray can. So that is why it is somehow very hard. Okay, so this particular force over the same area, okay, this force over the same area gives it more pressure. Okay, it gives it more pressure. The collision of these gas particles over the same area gives us more pressure, like the one that you have right here. Okay, so it's very hard. Okay, now one of the application of this law is the use of the spray can. Okay, the use of the spray can that they have right here. Okay, now okay, so as we write the Gay-Lussac's law, so as I've said earlier, that P, or the pressure is directly proportional to temperature, so it comes up like this. Okay, and now what we have right here is the real life example of Gay-Lussac's law. Okay, so number one, I've said already, the pressure cooker. The next one is the tire. The reason why people give allowance, okay, the reason why people give, or the drivers are gives an allowance to their tires before they drive, it's because when the tire heats up, the gases inside expand, therefore increasing also the pressure. Not only it increase the volume as you increase the temperature, but also the pressure as well. Also with the aerosol can, okay, the one that you have right here, this is the reason why you do not want to throw this one on fire. Okay, you do not want to throw this one on fire, because as the pressure, all right, so as the pressure on this can increases, it will explode. Okay, so it will explode. Now if you notice, if this can is empty, okay, if this can is empty, the temperature, all right, the temperature inside this can is also when this can is empty, the temperature is lower. You can feel that the can is cold. Alright, you can feel that the can is cold. Okay, so when it is cold, the pressure also is lower. So that is why it tells us when your spray can is cold, when the temperature of your spray can is cold, it tells you that the spray can is empty. Okay, the spray can is empty. It will not when you spray it, when you use it, it will not bring out any more paint. Okay, it will not bring out any more paint. So that's the effect of that smaller temperature, because your can is empty. Okay, so that's the aerosol can. Okay, so that is the real life example of Gay-Lussac's law. Okay, now let's work on some sample problems about this gas law that we have right here. Alright, so we have here the first gas law problem about Gay-Lussac's. Alright, so 3.0 liters of flask of oxygen gas has a pressure of 115 kilopascal at a temperature of 35.0 degrees Celsius, or okay, it was converted already, 308 Kelvin. What is the pressure when the temperature was raised to 100 degrees Celsius, or 373 alright, not degrees. Not degrees, Kelvin. Okay, not Kelvin, that is the thing there. Okay, so let's answer this question. Okay, the 3.0 liters here has nothing to do with the problem. Okay, so we have the pressure 1, 2, temperature 1, temperature 2. Okay, let's write down all the variables that we see on this problem. Okay, so we have here the pressure 1 is okay, so as far as I can see here, that is 115 kilopascal. Okay, so what we are looking for is the new pressure, because we increase the temperature. This is the initial temperature, this is the final temperature. So we have 308.15 Kelvin, and on the other hand we have 373.15 Kelvin. So the pressure is the second, or the final pressure, is unknown. Okay, so let's take a look. Okay, we were going to use the formula given to us by Joseph Louis Gay-Lussac. So we have P1 over T1, P2 over T2. Okay, since we have missing pressure, okay, so since we have missing pressure, so P2, okay, P2 is equal to P1 times T2 over T1. Okay, so let's plug in all the variables. Alright, so do we need to change the pressure into Pascal? Or something like atmosphere? Do we need to do that one? Okay, the answer is no. Because the problem didn't ask us to do that. Okay, so we don't need to convert this one anymore. Okay, so we have kilopascal, then the temperature too will be 373.15 Kelvin. Alright, so over 308.15 Kelvin. So cancel the temperature or the unit. So we have the pressure too is, okay, so as I compute this one, 5 times 373.15 divided by 308.15. So the answer is 139 kilopascal. Okay, is the new pressure of the flask. Okay, so this is the complete and final answer. Alright, so this is the complete and final answer. Now, let's take a look at the answer if the answer makes sense. Okay, in the first place. Okay, on the first one, the temperature was lower compared to the final temperature, which is 373. So we expect that at higher temperature, the pressure is also higher than 115. Okay, higher than 115. And after computing, we got the same, or we got the result that we are expecting. It has a higher temperature at higher pressure rather at higher temperature. Okay, so let's take a look at the second problem. So did you get it right? Okay, write it down in the comment section. Write your response in the comment section if you got the right answer. Alright, so we have here the second problem for our Gay-Lussac's law. Okay, again, you can pause this video if you want to answer this problem independently, and play it again if you want to find out if your answer is correct. Alright, so let me read the problem that we have right here. So a tank held nitrogen gas at 784 millimeters of mercury. When the temperature of the flask is set to 57 degrees Celsius or 330 Kelvin, what is the pressure, or the pressure is 642 millimeters of mercury. What is the original temperature of the tank in the first place? Alright, so this is a very tricky question. Okay, now if you are not quite sure about the variables that you have right here, make sure that you read it several times if necessary. Okay, so let's analyze this problem. Okay, so we have P1, T2, T1, and T2. Okay, there you go. So, based on the problem, in the first place, the tank has a pressure of 784 before it was changed to certain temperature and becomes like this. Okay, that's how the problem looks like. Okay, so 784 millimeters of mercury, and final pressure after the application of this temperature is 642 millimeters of mercury. Okay, so what will be the T1? Alright, what will be the T1? Now, based on the problem, it was asked on the problem that we should look for that original temperature. And definitely, this is unknown. Okay? Now, what is the second, or what is the final temperature? This one, in which you applied to become the pressure like this. Okay? So we have 330.15 Kelvin. Okay, so the formula that we will going to use is P1 over T1, then P2 over T2. Okay, so let's find out. Since we are looking for T1, alright, so since we are looking for T1, so the formula will become P1 times T2 over T2. Okay, there you go. So let's plug all the necessary variables that you have right here. So we have 784 millimeters of mercury times 330.15 Kelvin over what is the P2. So we have 642 millimeters of mercury. Okay, so there you go. So we have 784 times 330.15. Okay, divided by 642. All right, so the answer is 403 Kelvin. Okay, so that will be your temperature. One is the original temperature. Okay, temperature of the flask. Okay, so temperature of the flask. So that will be our answer. So 403 Kelvin. So let's take a look if our answer is correct. Okay, let's take a look if our answer makes sense. Okay, so what do we have right here? Okay, on P1, alright, so on P2, P1 is greater than P2. Okay, so definitely the temperature there is like that. Now, if the temperature is low, okay, if the temperature is low, then the pressure is low. If the pressure is high, we expect that our answer is also high. The temperature is also greater. So, the answer here is 403, which is, it makes sense. It is the original temperature is greater than the final temperature that you have right here. So, definitely, our answer makes sense. Okay? So, that was the Gay-Lussac's law. Alright? Alright, so now that we have all the three concepts, okay, that we discussed a while ago, so we can now find out what is this combined gas law looks like. Alright, so, okay, if we combine all the three relationships from the three gas laws that you have right there, from Boyle's, Charles, and Gay-Lussac, we can develop a definite mathematical equation that uses these three variables that you have right here: the pressure, volume, and temperature. Alright, so as we recall, okay, pressure and volume is inversely proportional to each other. Alright, and volume over temperature, they are directly proportional. And also we have pressure and temperature, which is also directly proportional. So what will happen if you mix them up together, or if you combine them together? Alright, so that's the whole idea, or will the whole idea of the gas law that we talk about Boyle's law, Charles' law, and Gay-Lussac will change? So let's see. Okay, so by combining all the gas laws that you have encountered, the three of them, okay, coming from Robert Boyle, coming from Jacques Charles, and coming from Gay-Lussac or Joseph Louis Gay-Lussac, we combine all of them, those three variables, to become one definite gas law that we have right here, which is called the combined gas law. Okay, so this is the formula for the combined gas law. We have P1 V1 over T1 is equal to P2 V2 over T2. Alright, so definitely the statement behind this combined gas law is that as the temperature increase, the kinetic energy of the molecules increases. Therefore, it will increase also the pressure, the amount of collision of your gas molecules to your container, and also the volume. As the molecules increase its speed, the volume of your gas will also increase when the temperature is increased. So definitely pressure and volume is directly proportional to your temperature. That is what the combined gas law is all about. Alright, so thanks to Robert Boyle, Jacques Charles, and Gay-Lussac for their contribution for this combined gas law. Alright, now the question is, can you use this combined gas law in solving Boyle's law problem? Yes, we can use this. Also in Charles' law problem, we can use this, and also in Gay-Lussac's. Now, what is the application of combined gas law? What is the application of the combined gas law in real life? Alright, so refrigeration system uses combined gas law. Okay? Hot air balloon, cooking of bread, okay? Our lungs, including the lungs itself, we use the gas law. Okay? We use the combined gas law. Alright? The air inside the tires. Alright? So it uses combined gas law. Okay? And many more. Alright? Okay? So also our weather system. Okay? Our weather system is heavily dependent to this gas law that we have right here. The movement of air. Okay? In our planet. So it uses the idea of your gas law. Okay? So the combined gas law. Now, we will solve some sample problems that we have right here. Okay, so prepare your scratch paper and your calculator as we solve some sample problems related to the combined gas law that we have right here. Okay, so for the first problem that we have right here, these are the given. Okay, so these are the given variables. So we have V1, V2, then we have P1 and P2. Then the premise is the temperature is equal. Okay, so the temperature is equal. So we will use the formula. P1 V1 over T1 is equal to P2 V2 over T2. Okay, so let's find out what formula are we going to use here. Okay, so since P2 is missing, so we will use this formula. P2 is equal to P1 V1 times T2 over V2 times T1. Okay, so definitely this is the one that we will going to use. Now, since the temperature is equal, we can safely say that this is a Boyle's law problem. Okay, this problem is a Boyle's law because the temperature is equal, so we can cancel this one. Alright, so we can cancel the temperature before we start computing. Alright, so let's plug in all the value that we have right here. Should we change the volume? So no need. Should we change the unit of the pressure? So again, no need. Okay, so pressure 2 is equal to 101 kilopascal times the volume 1. Okay, so the volume 1 was 50.0 ml over 12.5 ml. Okay, cancel the liters. Alright, so let's cancel the liters. So we have 101 times 50 divided by 12.5. Okay, so the answer here is 404 kilopascal. Okay, since we don't have any word statement, okay, so P2 is 404 kilopascal at constant temperature. Okay, so let's take a look. Okay, let's take a look. At constant temperature, what happens to the pressure if you decrease the volume? Okay, once you decrease the volume, the pressure increases. So it makes sense. Okay, it does make sense, the answer that we have right here. Okay, so that is question number 1. Okay, did you get the right answer? Okay, so if so, let me know in the comment section below. Okay, so let's go now to question number 2. Alright, so in the question number 2, the variables that are given here are the following. So we have 0.1 liter of initial volume, and we have a temperature already in Kelvin. Alright, so already in Kelvin. So because combined gas law uses Kelvin, not Celsius. Alright, so it doesn't use Celsius. Alright, so we have right here 463 Kelvin, okay, as a final temperature, and at equal pressure. Alright, so what is the volume 2? Or what is the final volume? Now, this particular question that you have right here is a Charles law problem because it has a constant pressure. Alright, so this is a Charles law problem. So let's put the formula. Our P1 over is equal to P2 V2 over P2. Okay, so since we are looking for V2, so we can safely say that V2 is equal to P1 V1 P2 over T1. Alright, so over T1 and P2. Okay, so this is our formula. Since the pressure is equal, we can cancel this one out. Okay, so since the pressure is equal, we can cancel this one out. Now, let's plug in those values. Alright, let's plug in those values. So, we have, okay, so 0.1 liters. Okay, so should we convert the liters? No need. Okay, no need. Okay, next one, we have temperature 2, which is 463 Kelvin over what is the T1. Alright, so we have 298 Kelvin. Okay, so what is the answer? So 0.1 times 463 divided by 298. Okay, so that will be 0.155 liters. Okay, that will be your V2. Okay, so let's take a look if our answer makes sense. Okay, now at this kind of temperature, which is lower than the final temperature, we expect that the final temp or the final volume should be higher. Okay, should be higher than the original volume. Okay, so we expect that the answer on volume 2 or final volume is higher than this one. So, we get our answer, and the expectations or the results of our answer is aligned to our expectations. So, it has a higher volume. Okay, the answer has a higher volume compared to the original one. Okay, so that is the question number 2. Okay, so next, question number 3. So these are the variables for question number 3. Okay, so let's take a look at the answer on the question number 3. So we have P1, 150 kPa or kilopascal. So P2, 250 kilopascal. Then T1, we have 308 Kelvin. So unfortunately, T2 or final temperature is missing. And we have a constant volume. Alright, so volume is equal. Volume, final volume and initial volume is equal. So what is the formula that we were going to use here? Okay, so let's write down the combined gas law formula. P1 is equal to P2 V2 over... Okay, there you go. Alright, so since we are looking for T2, so we have T2 is equal to P2 V2 T1 over P1 and B1. Okay, so this is our formula, and let's plug all those variables. Since volume is equal, so we can cancel them. Okay, so we can cancel the volume. Okay, let's take a look at this. Okay. So temperature 2 is don't forget to convert it into Kelvin first, ha. So it was converted into Kelvin beforehand, so we don't have any more problems here. Okay, so P2, so we have 250 kilopascal times P1, which is 308 Kelvin over what is the P2? So we have P1. So we have 150 kilopascal. So cancel the kilopascal, and we are looking for the Kelvin temperature. So T2 is 250 times 308 divided by 150. Okay, so the answer is 513 Kelvin. Okay, so let's see if this answer makes sense. Okay, so this is a problem of Gay-Lussac's law. Okay, this is a problem about Gay-Lussac. So kasi because the volume is equal. Okay, the volume is equal. Final and initial volume is equal. So if we increase the pressure from 150 to 250, we expect that the temperature also will increase. Okay, we expect that the answer is greater than the final temperature is greater than the initial temperature. So this is our answer, and we got what we expect. Okay, so we got what we expect. 513 is greater than the initial temperature. Then we are correct, 513. Okay, so that is question number 3. Okay. Next, question number 4. All right. So any more? We don't have any more equal here. Okay. So what if all variables are not equal anymore? Okay. There's no constant. Okay. There's no variable that is constant anymore. So what will happen? Okay. So again, we can still solve this one using the combined gas law. Okay. So we have P1, V1, P1 is equal to P2, V2 over T2. Okay, so as you can see on the problem, we have pressure 1 and 2. Okay, in kilopascal. And temperature, we have 293 Kelvin. It was converted already. 308 Kelvin. It was converted already. Okay. So the volume is 5 liters. Okay. Unfortunately, we don't have second volume. Okay, or the final volume. So that is the problem. Okay. So final volume is equal to P1 V1 times T2 over P2 times T1. Okay, so this is the formula that we will use. Okay, so let's plug in all the value that you have right here. I am going to use 308.15. All right, so I will be going to use 308.15. Okay, so we have V2 is equal to 100 kilopascal multiplied to 5 liters times T2, which is 308 Kelvin. Okay, or rather, I forgot the 0.15. All right, so 308.15 Kelvin. Okay, over 90 kilopascal multiplied to 293.15 Kelvin. Okay, so these are the things that we have right here. So first, before you compute, cancel all the similar units. Cancel. All right, cancel. And we are looking for the liters. Okay, so volume. Okay, so we have, we need to do it one step at a time. So 100 times 5 times 308.15. Okay, so the answer here on top is 154.75 liters over 90 times 293.15. Okay, so the answer here is 26,038 3.5. Alright, so there you go. So that is the thing that we have right here. So okay, so we have the second volume will be, or the final volume will be 154,075 over 26,383.5. Okay, so the answer will be, alright, so the answer will be 5.84 liters. Alright, so that will be 5.84 liters. Since we don't have any more statement on the problem, so this is the final answer. Now, does this answer make sense? Yes, it do make sense. So if you're going to take a look, so as the temperature increases, the volume should increase. Okay? We expect that the volume should increase. Alright, even though the pressure decreases. So it means that when the pressure decreases, the volume will increase. Okay? So the volume will increase. So technically speaking, based on our answer here, we expect, okay, the results of our answer is based on our expectation that the volume should increase when the pressure decrease and the temperature increase. The volume should increase. Okay, so that's how it works. Okay, so did you get the right answer? Okay, so let's go now to the question number 5. Okay, so these are the variables or the data given to us. Okay, so again, in P1 we have 800 and 100 kilopascal. Okay, so V1 is 1.0 liters. And we have T1 and T2, 303 for T1, 298 for T2. Both in Kelvin. Okay, both in Kelvin. You cannot use Celsius here. Again, reminder, you cannot use Celsius here. Okay, so what is missing is again V2. Alright, so which tells us that we will compute now. Okay. Okay, so this is the formula. Okay, and the V2 is P1 V1 times T2 over P2 times T1. Okay, so that will be our formula for this problem. Okay, so let's plug in all the variables. Okay, so we have 800 kilopascal. Alright, times the volume, which is 1.0 liters. Okay, and temperature 298. Alright, so I will include the 0.15 over here for our answer to be more precise. Okay, next one, P2. Okay, so we have 100 kilopascal times we have 303.15 Kelvin. Okay, so before you compute, cancel all the similar units, cancel, and we are looking for the liters or the volume. Alright, so we have the volume, and let's do it one step at a time. 800 times 298. So that will be 238 for 1,400. Alright, liters. Okay, so we have 100 times 303.15. Okay, so we have 30,000. Yeah. Okay, so we have this volume. Okay, so 238,400 over 30,315. Alright, so the answer is 7.86 liters. Alright, so since there's no statement, then we don't need any completing statement for this problem. Now, again, let's see if our answer is or does make sense. Okay, now the pressure decreased from 800 to 100. So the pressure decreases. So it tells us that when the pressure decreases, the volume increases. So, okay. Next one. The temperature. Alright, so the temperature that you have right here. Okay. The temperature that you have right here is decrease. Okay, the temperature decreased. Okay, somehow the decrease in temperature is very minimal. Okay, from 303 it becomes 298. So we expect that the volume is somehow less. Okay, it is somehow less than or lower. Okay, but this is the thing here. Okay, since this one is since the pressure has a greater value that you have over here, it has a greater decrease. Okay, it decreased too much for the pressure rather than for the temperature. So we can see that the volume here is somehow leaning towards the increasing side rather than the decreasing side over here. The Charles law tells us that as we decrease the temperature, the volume decreases, right? So even though that's the situation, we have here the pressure over here, which is very low. Okay, from 800 it was decreased to 100 drastically. So we can expect that the volume is increased drastically as well, even though the temperature is very low, or somehow even the temperature is somehow low. Okay, so the answer is 7.86 liters. So it is greater than the original volume. Alright, so that is question number 5. Did you get the same answer? Okay, so did you arrive with the same answer as mine? So let me know in the comment section below. Alright, So finally, we have the last problem. Okay, question number 6. These are the given values. Okay, again, we have the same problem here. Volume is missing. Okay, why volume is missing? Because we can easily compare it. We can easily compare it with the pressure and then the temperature, the relationship among them, and easily find out what is our expectations. Okay, so again, in pressure, we have 6.5 and 0.95 atmosphere. Should we change this one into kilopascal? Because on our previous problem, we used kilopascal. So no need. Alright, so no need for us to change this unit. Next one, how about the volume? We have 2.0 milliliters. Do we need to change it into liters? No need. Alright, so no need to change it into liters. Alright, next one, how about the temperature? It was changed beforehand. It was converted beforehand, so 283 and we have 297. Alright, so let's take a look. Now, if we're going to analyze this problem, the pressure is very low. Okay, from 6.5 to 0.95. So it was decreased. Also with the temperature, it was also, in the temperature side, it was increased. So meaning to say that the volume should increase. Okay, the value of the expected answer here is greater than the original volume. Alright, so let's compute. So P1 V1 over T1 is equal to P2 V2 over 2. Alright, so again, the volume is missing, so we can have this formula. P2 over, we have P2 top and T1. Alright, so yeah. Okay, so we have V2. Then let's plug in all the values that you have right here. So we have 0.95. We have 0.95 atmosphere. And V1, we have 2.0 ml. And we have on the temperature side, so T2, we have 297.15 Kelvin. Alright, so over. Okay, so over, what do we have right here? P2. Or rather, 6.5. So let me change this one. This is 6.5. Alright. So that is 6.5 and 0.95 below. Alright. Multiplied to T1, which is 283 Kelvin. Or, I forgot the 0.15. 0.15 Kelvin. Okay, so we are now good and ready to go for the computation. We will do it one step at a time. So 6.5 times 2 times 297.50. So the answer there is 3,862.95 ml. Okay, by the way, I forgot to cancel out all the units. Right, so there you go. Alright, so let's take a look at the one at the bottom. 0.95 times 283.15. So that will be 268.9925. Okay, so I included all the decimals so that the final answer will not be affected. Okay, with the significant figures that we will have. Okay, so we have the final volume. Let's see if the final volume will increase, okay, at a lower pressure and at a higher temperature. Alright, so let's compute. So 3862.95 over 268.9925. So the answer is 14.4 ml. That will be your volume. Okay, so let's take a look. What do we expect? We expect in the first place that the volume should be higher. Alright, should be higher than the original volume. The final volume should be higher than the original volume. So, we get what we expect. Okay? That's it. Alright, so this is the combined gas law in its sample problem. Alright, so don't forget always to always convert the temperature. If the given temperature on the problem is in Celsius, always convert it into Kelvin. Alright, that's the key here. Now, if you didn't convert it into Kelvin, it will affect your answer at the end of the day. Okay, so the units for the pressure, okay, you will just convert the units if the pressure units are different. For example, this is atmosphere and this one is Pascal. Example. Okay, so you will convert this one. Okay, definitely. Another one is for the volume. Okay, if the volume 1 is ml and the volume 2 is liters, so definitely you will convert that one. So that they should have 1 unit before you compute. Okay, before you compute. So there should be 1 unit. Okay, for cancellation processes or purposes. Okay, so that is the combined gas law. Okay. And that ends up our topic for this video lesson about the combined gas law. I hope you'll be able to get the value on the topic we discussed today. And if so, don't forget to like this video. And if you have questions and suggestions, write them down in the comment section below this video. It will help me a lot in the algorithm for my YouTube channel. Most importantly, don't forget to subscribe to my channel and hit the notification bell for you to be updated for more science video lesson in the future. Okay, so I'll see you next time, everyone. Enjoy learning and practice always. Stay safe and peace out. Peace out.